All right. Okay, my name is Alankar Sharma from Comcast. Um, I'm data center architect there, responsible for design and strategy for national, regional, and local data centers. Um, I would also like to introduce Tony P. Tony, are you around? Over there. So Tony contributed a lot to this, and Tony is also author and editor of the new data center routing protocol, Routing in Factories, RIFT, dealing a lot with IETF on the topic. And thank you, Tony, for taking time to come out here, and he'll be happy to answer any of the questions. So let's quick background on like why routing in factories, what are we trying to do, why we are here, the motivation behind it, and like why is there a need for something else? So little background, few years ago, some of the major companies and Comcast as well, due to the complexities, the scalability issues on IGPs, ISIS and OSPF made a move to BGP-based data centers. We did it very well. It was great for the time. We made network much better. The stability in the network, the reliability, we came pretty far with that, but over time, as things evolve, and I know most of the network guys know, in production environment, we keep building things on top of what we have built. It's like stacking, building a tower, putting another box, another one, and when you get to the top, it's not, if you need to change the foundation, it's not easy to go back and retrofit. I mean, these brownfield production environments are pretty rigid, and oftentimes things come in as, oh, we just need this, this is temporary. And we know how long those temporary things stay in the network. Most likely until end of life or until it breaks. So we started building BGP, we went following the best practices, but as we move forward, we realized, well, this is protocol, the foundation built for different purposes. I guess everyone knows what BGP was built for, but as engineers, we got creative and we were able to fit it in data centers, and it was good for the time. So we'll go through some motivations, how things evolved in network at Comcast, and then talking with others, I hear the same stories. So we'll go through those challenges and what Rift offers us. We'll go through that. And it's new, so we hear, well, why is there a need for new? We can hack BGP, we can do this, yes, we can. But it reminds a story of one of my friend, Dominic, who is a rich guy, but he has old car, and he sees, oh, some new feature came out, like GPS came out. He says, oh, you know what, I can buy that off the shelf, and I can fit it in my dashboard or wherever the GPS goes. Why do I need, my car is as good as new? So we'll go through those things as well. Let's take a quick look. So get started in the slides. This is from when I started networking. I wasn't there at time of ARPANET, DARPANET. When I started, it was networking, and over time, I realized we have IPv4 issues, and people started using NAT, and we made it we made it networking. We went further, and I guess we all came to the point where we see, well, it's too much NAT, and some places it doesn't work, and came out to almost where it's kind of not working, and there you go. Well, we need to make a switch. We need to go to IPv6. Now you need something new. So let's get into the BGP stuff. So RFC 7938, about 4 years ago, BGP data centers, major companies built it. So here's the typical topology, leaf spine architecture, where the top of rack leaf device, then some aggregation layer, uh, super aggregation and bunch of different aggregation levels. And the typical design was, okay, from the north, we are sending default down, and from the south to north, it's sending this more specific routes. At the end result of that was, if I log into my Leaf device and if I do show IP route, I see only one route. There's only one default. There's not, the troubleshooting is much easier. There's not much state. So that, that was good. In the design, again, the Leaf devices, they are all running same AS number. There are different choices. We chose to run same AS because we didn't want routing from one Leaf to reach to the other one, those routes, because the BGP same AS loop prevention mechanism. And so every layer is running its own AS. And there's a small comment on the left side where it says policy ACL. We'll get to that later, but just wanted to make a comment. So the policies, the access control was done on the Leaf devices. So this worked great, but something we realized, if we follow the typical class architecture, the top devices, if they lose a northbound connectivity, which was the top in our topology going to backbone, we lose the in-band reachability over the loopback IP. So for certain people, the mindset was, well, this is not a problem because it's not impacting your production traffic. This is all for management, and your production is not impacted. But if you look from operations perspective, or for any other inbound telemetry or any other polling or any other management stuff, the device is not reachable. So it's a problem for ops. Now, again, you can fix it by breaking the class design, by creating east-west links, running IBGP and certain things. So that's kind of it's a small problem, but something against the pattern. But that's okay. That didn't bother much, and we keep moving. Now, over time, we needed to build some centralized services, some service chaining kind of stuff in the centralized zones. Quick example is load balancer, and we took some central position in the network topology, created those services, and that is when we started feeling, okay. But again, things worked. These are all mostly source-netted devices, so layer 3 routing, it was working fine. But over another year, now we ran into other issues. The policies on those top-of-rack boxes, people had different issues. One example for what we went through was those top-of-rack have limited TCAM, and the ACLs just went up to the ceiling. We could not have ACLs. In security requirements, well, we need some stateful inspection. So we had to have something like this, which is kind of, it's the same services zone, but it grew bigger with like some policy devices in the middle in those central zone. And you see those ACL and the policies are not there on Leaf anymore. So the traffic is all passing through those central policy enforcement points. Now, what that brought is not only the traffic, the routing all the routes have to pass through that central zone. That means the routes coming from north, following BGP, go down to that central zone and come back up, and then go back to the Leaf again. So that's where we ran into, okay, you have route coming down from one device and going back up. Just for clarification, we used VRFs. So the internal and external side of that, it's coming in one VRF and going back in the other one. So now when the BGP route came from AS number XYZ and loop back or go back to the same device XYZ, it's not accepted there. So again, all this stuff in testings we found, now we need to fix that. So again, engineers came up with, okay, how about, BGP gives us all the knobs to tweak it, to hack it, and we went, okay, let's do allow ASN, and we can get the same routes back in. So we tried that in lab. Again, if you do that, you break the loop prevention, some basic BGP stuff, and by doing that, now you have all the routes all over the place. So we said, okay, BGP also gives us the filtering. So we go create route maps, do some policies, build route filtering there. But then at that point, you need it on every single device. Hey, I want to accept default, and I don't want to accept those. It's all static configuration all over the place. And yes, it can be automated, but in my opinion, it's no different than just having static routing. I mean, you are programming every single route what you want where by policies. And at the same time, when I talked to Dominic, he was like, oh, I see new cars came out with Bluetooth systems. So he went outside, he bought the Bluetooth, and he hooked it up in his car, and he's like, oh, now my car has Bluetooth. So we are fixing things. So with allow ASN and the policies, again, it's not clean. So what we came up is, okay, the problem is the AS path. The BGP carries that path information, which is breaking, these same routes accepted in, when it's going back in the same layer. So how about we just remove the path information? How about we erase it? So that kind of seemed good, because again, there are so many options here. So we hacked into BGP and we said, okay, we erase clear AS path, so there's no path history at certain points, and we start fresh from that point all the way until it's needed to the next level. So, and that's where pretty much we are today. It's operating fine. It's working. And when I talked to Dominic back, he says, oh, you know what? These cars have backup cameras, and I'm going to buy that, and he fixed backup camera. And so his car is still great. So going into, here it kind of highlights the flow that I just talked about for how the routing is working. So if we look from the top, there's default down going through AS layer, going to the services zone, and coming back in the VRF to AS, because those are logical links, back to service spine, and going to top of rack. So you could easily see the AS path on the left side in those numbers, 65001 to 2 to 4, 5, back to 2 and 3. So some repetitions, and that's where we had to do allow AS in and clear AS path. Then as we moved on further, these are the problems where we are today. My software group, they say, oh, I need your whole link state. I need to know which links are up, which are down. So you got to send me link state. I don't have link state there. I mean, how do I do it? Then do I run another IGP now just for the link state? Anyway, so that's one of the missing features that I don't have hack in BGP today. So going through all those things, one after other, it's like, well, we are working, it's kind of anti-pattern for what we need in data centers. And the leaf spine class architecture is so widely deployed. It's unique and it's deterministic. Why not build something that really works for that, what fits for that architecture? So that's where the Rift came up. But just to summarize the points, what we talked as the problems, the issues with loopback reachability, the AS path, we erase it, allow AS in, setting policies, there's no link state. This configuration is all, yes, you can automate, but typically it's static config, define neighbors, define all kind of statements. And so like, in the end, what we are trying to do is we are trying to take this eBGP or some exterior protocol and make it behave like IGP. And we say it works. So this is kind of how we make it work. It's so close to where we are at a point, well, anyway, just a description of config. So on my devices, I have thousands of lines of BGP config, whether it's coming through some automation or some human doing it or copy paste, whatever, but there are thousands of lines of config. Whereas if we do something new, we have option to build it ground up, and what we have in routing in fat trees, it could be as simple as one statement, and it does things for your topology. So what is Rift? Routing in fat trees. I was asking my vendors to, hey, can you do these things in BGP? Can you make some extensions or those modifications? Worked for almost 3 years, and when we sat down together, it's like, well, those changes are too many, and if you do all of that, then it's not behaving like BGP anyway, like making neighbors coming up like OSPF. And we kept going on, and then I met Tony, and we shared pretty similar mindset. Yeah, you know what? It's time to reboot. It's time to have something better. So a quick introduction on that. So Rift is open standard draft in IETF. There's a formal working group working on it. It's built for class architecture. The basic points are that leaf spine is pretty deterministic architecture, so we can make certain assumptions, certain enhancements, modifications to have a protocol which is built or well suited just for that, rather than having other ones which are great. They are great they work in all kind of topologies, regular ones too, like internet topology. So let's go through some of the high-level points. And I was told to keep the session pretty high level, because I mean, if you need more details, the specs are out there on IETF working group document. You can read that, and any questions for in-depth stuff, we can take that later. And Tony is here as well. So before we do something new, it's like, what's the difference? Why do I need it? So we'll pick some of these, the interesting ones I found, but as a summary, we took, okay, BGP is great and all the IGPs are great, so why don't we take the best of both worlds? We took the best from distance vector protocols and best from the link state, and we made a hybrid. So the way it works is it talks distance vector down and link state up. We took best from both of those. And at the end result, it minimizes the routing state on any single box. The pattern we saw that we wanted, that we made BGP to work, was through some policies we send default down and specific north. That routing in fat tray does by default. That's the natural behavior. It does what. So instead of tweaking something, it's coming naturally here. It has the concept of topology awareness, because the class architecture, the leaf spine is deterministic topology. So based on, it's always going to be in that kind of topology. Certain assumptions could be made and optimizations could be added. So smart disaggregation, we will go through that in slides. Unequal cost, multipathing, we'll go through that. Load balancing on some failure of northbound nodes which are not directly connected to you. The route reflection, flood reduction, autonomous, we'll go through those, so we'll save time here. And other common features which are not in detail described here, but they're all out there. And I made these slides a couple of weeks ago, so things are moving fast. There's new draft that came out on June 21, certain other things added. But the common things that you would expect are there, and if there are some more things, anyone feel free to contribute. It's open standard draft. So, okay, taking a quick look at the class, the topology. So this is how it looks like. The bottom layer, those racks of servers with top of rack switches on them. So every layer has some kind of level assigned, and it's just a number. So for this purpose, I'm taking here as 0. Next level, spine, or whatever you call it, level 1. Next, some aggregation layer, level 2. Next, level 3. So that level brings the concept of topology awareness, where I sit in my whole aggregation layers. So we will get to the levels again in towards the autonomous routing concept, but I took some of the simple and distinguishing features here. So one of the things, enhancement that was added is smart disaggregation. So if we look here on the top diagram, we are getting default down from spine 1 and 2 to switch 1 and 2. So if switch 1 network 10.x something has to send to 192 something, it's going to send half-half to both the spines. So that's the steady state. If the link, as shown in the lower diagram, if that link goes down, typically what we have today, we will still keep sending because we are still receiving default. That's how we are operating with our BGP today. But with the Rift, it knows, okay, that link went down. It would do smart disaggregation. So switch 1 knows, well, spine 1 knows spine 2's link went down. Spine 1 will send more specific routes, 192 something, to switch 1. So now if switch 1 has something to send out to 192, it will never send to spine 2. For everything else, it would still keep the load sharing. The route reflection concept. So the biggest thing that I heard from most of the engineers around, well, and some engineers who have been out there for more than 20, 25 years, hard to get like, oh, so what is, I don't have east-west link, I don't have cross links there. So typically, like, people, when they were making diagrams, they always had interconnection. But in the class architecture, we don't have that, and it's not really required. But then how do we get the state across devices in the same layer? So we added a route reflection mechanism, real simple here. So the layer in the middle, spines, they send their adjacency information to the leaf devices, and they reflect it back north to one layer up. So because of that route reflection mechanism, now we have same link state information on the same layer of devices. Otherwise, we would have to have east-west links. Now, this also helps with the first problem that we brought up, the loopback reachability issue. Again, it's a minor issue, but if you lose the northbound links, the local IPs from that device, loopback or anything else, could be reflected back from south, and you have that reachability from the south. Flooding reduction is it's kind of a hot topic, and one of the major challenges why people wanted to move from OSPF or ISIS to BGP to have, because they are in large scale networks, it's flooding everywhere, and it's too much, it's too chatty. So this is recent addition from different vendors and different people coming together, contributing, and very elegant loop, very elegant flood reduction mechanism. So at high level, leaf 1 at the bottom will choose its flooding leader in the upper layer. The way it chooses is based on the level of connectivity it knows about the north box, and running a hash through it, and it says, okay, whichever box it could be. In this diagram, it shows spine 1 as the flooding leader. So spine 1 will send those updates to northbound, and there's also second one for redundancy. Spine 2 is the backup flooding leader. So you have two updates going for for each prefix. Now the elegance here is, it's not always, all the nodes are not going to choose the same flooding leader. It's kind of distributed. Some leaf 2 or some other device may choose someone else. So it's just distributed all over the fabric. So you're not running just one device as your designated router and updates going just through that, running that link as hot, or even if it's a large number of updates, it can impact your convergence times as well. The bandwidth balancing, again, everyone wants to use links efficiently, and we use our links 90%. Utilized. It's not one is 10%, other one is 80%. So there's some inherent bandwidth-based balancing capabilities. Again, high-level quick example. This is a kind of real-life example here. From the top aggregation box, it's getting default from upstream, and it's ASO1 advertising default down. So typically in steady state, you will get 50% traffic on 1, 50% on 2. But if we lose the link, as shown here, from ASO1 to the backbone, typically you would still keep getting 50-50, however you have reduced capacity. But here we can, it adjusts the cost, the bandwidth adjusts distance, saying, okay, I have half of the bandwidth. So that information passed down. Now, the spine layer S1, 2, 3, 4, they will adjust how much traffic they can send north. They will send 2/3 to ASO2, which has double the bandwidth, and 1/3 to ASO1. So that's the weighted ECMP behavior, some balancing on the fabric. Now, the autonomous routing, just because, okay, and I see I'm seeing the time limited. So in autonomous routing, each node can figure out what its role in the fabric is, what level it is at. It can self-discover that and start routing by itself. The only thing you need is a seed device, which can be at the top here. And based on that seed, it tells the lower level receive multiple advertisements of levels and say, okay, I received those many values, so I must be this. And it automatically figures it out. It does not need any ZTP or any kind of controller to push the config and tell. So it's not automated, it's just self-discovered. So fine, we have all that, so what? Now what do we do? So we move from this to that. Just quick summary here. So again, it's open standard. Everyone is, whoever interested, who is running Leaf Spine, bring your problems, feel free to contribute. It's encouraged. Specs are completely open. There's a working group working on it. Things are going fast, very well. Some new drafts are showing up for Yang and for other necessary stuff. Major vendors are on board. We have Cisco and Juniper working on it. And there's also a binary package available for download. And the next IETF also has hackathon organized there. So, all right. Any questions?
All right, thank you very much.